Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 30, part A. We're discussing the exponential distribution. So this is the first part of that lecture series. So last time we discussed continuous PDFs or continuous distributions, and we talked about a PDF, which is a probability distribution function, which denotes that it's continuous, and the CDF, which can be either discrete or continuous. So we can't use CDF to tell us what type of variable it is, random variable, if it's continuous or discrete, but we can with the PDF versus PMF. Okay, so we did the example of the uniform. We've talked about now using continuous methods, which are integrals. We've talked about the expected value, variance, the moment generating function. We also talked more about the continuous uniform distribution itself, all of the entire distribution. And we talked about how to calculate percentiles and quartiles for continuous distributions. In this section, we're going to talk about 3 different distributions. And so I'm going to take a lecture for each one of these, a lecture meaning one day to cover each of these distributions, which I think is a lot more reasonable than trying to cover this section in 1 or 2 videos, or 3. Okay, so I want to recall your attention to the Poisson distribution, which is discrete. The Poisson distribution deals with the number of occurrences or counts. So if you see something that talks about how many, then, or counts, that's the Poisson distribution. But this, if you remember back, we talked about it being on a fixed, continuous interval, either of time or space. And the Poisson distribution, as I said, was a discrete distribution. Now, the number of occurrences is not the only random variable we can get from these problems. We can either do the Poisson distribution for the counts, or we can do the waiting time, which is continuous, and between successive occurrences, okay? So, but the continuous random variables, and again, we can only assume a positive value for waiting time. All right, so waiting time has to be a positive value, and then with this, it can be a continuous type random variable. All right, so we're going to let W denote our waiting time, and until the first occurrence. This kind of reminds us of the geometric distribution, even though we were just talking about the Poisson distribution. The geometric distribution said we were going to continue our Bernoulli trials until we got or obtain the first success or the first occurrence of whatever we're interested in studying. Don't let the word success and failure fool you. In this context, success is just the category that we're calculating probability on, that we're answering questions about. I do work predicting mortality, and so predicting death, and I certainly wouldn't consider death as a success, but that's how I have to treat it as far as the formula goes. So don't let the word success and failure trip you up. Make sure that you understand that the category that goes with P for those discrete distributions is the category you're answering questions about. Okay, so let's get back to this. So we want the waiting time until the first occurrence during the observation of a Poisson process, in which the mean number of occurrences in the unit interval, whatever that is lambda. Remember, we did some Poisson problems where our unit interval was 10 minutes or 1 minute or an hour, so it can be whatever we defined as the unit interval. And so that's lambda, that is the mean of the Poisson distribution. But W, the waiting time, is a continuous type random variable. Since the waiting time is non-negative, the CDF, capital F of W, equals 0 when W is less than 0, because time can't be, we don't have a waiting time that's negative. It can't happen before we start waiting. And then for W greater than 0, we have the CDF is always equal to the probability that w is less than or equal to some value, in this case little w, which is 1 minus the probability that, and this sign should be a greater than, 1 minus the probability that w is greater than w. All right. And so what this stands for is we've got 1 here, 1 here. So what this here stands for is the probability that there are no occurrences in the interval 0 to w. This is stating that w has to be greater than little w, and we're talking about the first occurrence. So this is 1 minus the probability that no occurrences happen in the interval 0 to w. And we can write this using the Poisson distribution as 1 minus e, but now instead of lambda, it's lambda w. So we learned that if we change the unit of time or the interval, then we multiply lambda times that change. So in this case, it's w, okay, for the length of the interval. 0 to w is w. So for the Poisson distribution, remember that probability that x is 0 is equal to e to the negative lambda. And that's where we get this right here, this equation or this form, part of the formula, is from the Poisson. But now instead of lambda, we're on an interval 0 to 1, we're doing that for an interval of 0 to w. All right. So the mean number of occurrences is proportional to w, and we learned that under the Poisson. So the probability that y is equal to 0 is here, and so I've worked through that for you. When w is greater than 0, then we can take the derivative of the CDF to get the PDF, and when we do that, we get this expression here. Now, what we want to do is we want a parameter that goes with the exponential distribution. So we're going to let lambda equal 1 over theta. This also means that theta is equal to 1 over lambda if you solve for theta. So the random variable x has an exponential distribution if its PDF is given by this form here. Now, we only need this part when we're given when we are expressing this with a theta, not an actual, the symbol theta, not an actual value. Once you put an actual value in for theta, it's going to be positive. There's no need to then put this portion here in our PMF or PDF anymore. Okay, but we always need that x is greater than 0. And so theta is now the mean waiting time until the first occurrence. Lambda was the mean number of occurrences the mean number of occurrences in the unit interval. So theta is the mean waiting time until the first occurrence. Okay, so let's look at the MGF, the moment generating function here. Remember that the definition is the expected value of e to the tx, and we write the moment generating function as capital M of t. And for a continuous distribution, it's going to be an integral from the lower limit, which in this case is 0, because that's what our limit here is, and we do it across the entire support of x, which in this case is up to infinity. And so anytime we have e of a function, the expected value of a function, that function and then times f of x, and that's integrated, and of course for the integral we have to have d of x as well. And so what we can do is we can combine the exponents here. Let me erase my messiness circling things. So I'm going to combine this exponent, and I want to factor out. I've got a strategy here that I need to do. First thing is I need the exponent to be negative, all right? Because then it's easy to see that this is 1 over e, and that helps when it comes to convergence. Remember, we have infinity up here, and we need this quantity to be greater than 0. We need this to be greater than 0 in order for this to converge to 0 at infinity. Otherwise, it diverges. So we've got to be careful with our conditions on t, actually, and we'll talk about that in a minute. So I want to write this in terms of x times or divided by something. So what I'm going to do is I'm going to factor out x here, Okay, so I factored out x at the back, and that leaves it as negative parentheses 1 over theta minus t. Now I can factor out the 1 over theta from both of these. From both of these. And that would be the same thing as multiplying both of them by theta and then pulling it out. And so I didn't do that, but you could do that. And I think the book does that. So if you see that's what they're doing. They're factoring out the 1 over theta. That ends up giving you 1 minus, inside the parentheses, it gives you negative 1 minus theta t x over theta. So that's another way of writing it. Now, we can use u substitution for this portion here, or you can just remember that you're going to divide by the coefficient, which is 1 over theta minus t, and we've got the negative in front. And so that's what I've done here in integrating it. Of course, e to the power still stays the same. It's from 0 to infinity. Now, this one's pretty easy. So when I, remember we have a negative out here. When I plug in infinity or take the limit, I'm not going to remain so stringent as far as our using limits and exchanging. Most statisticians or mathematicians don't take that extra step unless they're publishing, so that it's obvious they know what they're doing. But we know what we're doing now. We're going to take and put in infinity for x, or the limit as x approaches infinity. And what happens there is this is 1 over e to the 1 over theta minus t. And as long as this is positive, that goes to 0. And so here's our 0, and then we can plug in 0 for x, and that's going to be e to the 0, which is 1, and so that leaves us this, and we're subtracting, and that becomes a positive, and we're left with this expression. And so in order for the integral to converge, as I've mentioned a few times, this quantity has to be greater than 0. X is always greater than 0. That's our condition for the PMF. So it's left that the coefficient has to be greater than 0. We solve for t, and t has to be less than 1 over theta. Remember, theta is always positive too. So t is a positive number that's less than 1 over theta. Okay? And theta is usually larger than 1, but it doesn't have to be. And so this gives us our moment generating function, which, remember, is unique for each distribution. So if it has this form, and I have a negative 1 here, then it is the exponential distribution with theta as its parameter. Okay, so I think that's a good place to stop in this video. So don't forget to scan and upload your lecture notes before midnight of the date listed in the course calendar. Update your formula sheets with, actually you'll probably want to update your list of distributions in this case. Not definitions, distributions. So you want to update that for the exponential, create one, make sure that you include everything that's on there and some of the things that are in the worksheet. There's some facts that I've had you derive in the worksheet that will be handy for tests. Take care of yourself, and we will see you next time.